Thanks for the intro. It's great to be here in Canberra. It's been like 16 years since I was last in Australia as a high school student. This is a really impressive audience. I was at some of the talks yesterday, and the caliber is really up there. It's sort of always awkward being a hardware guy in a software conference because I'm like, where's the soldering irons and where are we talking about? So hopefully you guys have fun with my keynote today. So I'm going to talk a bit about making hardware, the processes and challenges of doing that, and then I'm going to go quickly over some of the issues that we encountered embedding Linux in the hardware, and talk about a couple case studies in terms of actual hardware applications of Linux that we've done. So this here is your typical Moore's Law curve. The blue line is a bunch of data points I harvest off Wikipedia of x86 processors, over time. And then I kind of eyeball over there the yellow line here, which represents the curve of sort of ARM processors simultaneously. The big thing is that the blue line would be processors that cost several $100s on their debut, and the yellow line is processors that cost about $20 on their debut and drop to single-digit prices very quickly. As you can see, since clock speeds have slowed down in recent years in terms of the growth of clock speeds, it's given a great opportunity for low-end processors to completely catch up with the desktop brethren. So now you can buy mobile phones that have quad-core 1.6 gigahertz performance, which is very similar to what would be inside of an ultra-low power netbook. This has really been enabling in terms of converging sort of the Linux and the desktop paradigm. So now inside your mobile phones and in your pocket and your walls and your desks and so forth, you can have full Linux machines. But this trend here is essentially what enabled me to do a startup around 2005 where we wanted to put essentially Linux everywhere. Back then it wasn't as common to have small Linux computers all around your house, and we wanted to build a company where we could bring the internet cloud to common appliances like alarm clocks, photo frames, TVs, that sort of stuff. This is just for those who aren't familiar with the product, this is the tech stack that we had running behind it. Most of the devices ran under Linux, and then on top of it we used Flash, actually, which turned out to be a really bad idea, but that was only in retrospect. Back then, you couldn't actually run WebKit. The WebKit really didn't exist when we started, actually, and then you couldn't run a web browser in 64 megs of RAM and a couple hundred megahertz CPU, so we were tempted to use Flash instead. And then on top of that we had some UI and then a whole layer of Rails and Apache and cloud stuff that hardware guys like me never touch, that I've seen in slides and I included so you guys could maybe enjoy it. This is a sampling of the Chumby devices that we had built. These three on the left here were ones that I actually had designed and manufactured myself. And the one on the right is one that was made by Sony, a partner that we had got together with. The progression of CPU speeds over time, of course, kept on going up. So did screen sizes. Of course, Sony decided to take a step backwards in CPU performance, which is why the UI performance really sucked on the device. And it's sort of unfortunate they decided to do that. Here's a bit of a little chart here that tells you how much time is spent actually making a product. So for the Chumby one, which is, it's that one right there, the little white guy right there. I actually went back through my emails and looked at, what date the emails were versus the general phase of the product that we're in. It took about a year to do the product. I'd say about a quarter of time was spent sort of doing marketing and studying biz dev. This is sort of emails to retailers, vendors, marketers saying, hey, would you like to have a $99 Chumby, and what would the features need to be? So, and then maybe only about 15% of the time was actually done doing actual hardware design, meaning schematic, PCB layout, and that sort of thing. About 20% of the time was sort of not really, it's unfair to say 20% was just for the software dev. What happened is software dev was going through the whole process. 20% of the time was the time required for software as a long pole in the tent to catch up to everything else before we could ship a product. About 10% was industrial design, and then about 33%, the majority of the time is spent in mass production ramp, which is things like organizing the supply chain, talking to factories, doing tooling, tweaking, fixturing, all that sort of stuff, which is sort of my latest obsession is trying to enable more people to be able to do that kind of thing. So I'll talk a little bit about the process of actually giving Linux a body, an actual shell, which I think is, I don't know how many people here have done injection molding. Has anyone done injection molding? A few people probably here and there? Okay. So when you want to design a gadget and you want to sell it, it's great to have bare boards, but consumers feel more comfortable when there's something around it. So I got better at building devices that have shells around it. So every design that you want to manufacture starts a very detailed 3D model. I mean, we would model the circuit board and the parts on it, all the connectors, all of the holes, cross sections, the clearances, everything would be all done in a 3D model environment. It's very important to make sure your connectors don't collide before you actually make your product. It's sort of unfortunate when it does, so we would take time to make sure that's okay. Make sure the LCD doesn't fall out, make sure the speaker boxes sound good and they're the right size and so forth. So we did a lot of modeling and CAD work. We'd agonize over small details like this. We would have hours of meetings, should we make this little detail a little bit bigger? Does it really express the right DNA and all this kind of crap? It'd take forever. Once you've gone through all of that, then you actually need to build these things for actually doing the injection molding. These are the steel tools that are used to do injection molding. Just for reference, this one's probably about the size of the table here. They weigh several tons, and they have to take really high pressure plastic and they force it into a small cavity and turn it into your injection molded part. This is what the tool looks like when you open it up. All those little pins there are what's used to force the plastic out of the cavity once the injection molding is done. And this is kind of an image of what the actual finished cavity looks like. The pins are actually, you can't see them because they're actually flush against the body right here, but they actually, when the part's ejected, a set of pins will come rising out of the mold to push the injection molded part out. To build these tools, you have to do a lot of steel cutting. They start in a tool shop that looks about like this. This would be a pretty big one. A whole bank of CNC machines on the left and a bunch of people with saws and mills and all that sort of stuff. And sort of floor-to-ceiling milling machines, which I always love going to factory tours. You can see these really big robots cutting steel and doing your bidding. Once you've done sort of the rough tooling part and you've kind of done a sort of a rough cutting of the steel, the finish isn't good enough. If at any seen tooled steel, you have these sort of little circles, little tracks of circles where the milling bit had gone. In order to get the fine finish, so if you look at a product that has like a satin finish on it or has small holes and so forth, they actually use a process called EDM. It's where they take coppered electrodes, and this is a collection of coppered electrodes, and they mount it onto the steel tool. So here the steel tool is on the bottom in a bathe of sort of tooling oil, and there's a copper electrode right there. And they force several hundred volts and several amps through it. And they actually use the sort of, the force of electrons actually flowing through the electrode to knock away atomic layers of steel. It's a very, very slow process. It takes like maybe 8 to 10 hours to put one feature in. But the finish is extremely high quality. It's down to half a micron precision. So tooling is a very, very, very time-consuming and very expensive process. Once the tools have been made, this is another example of a tool that's open. The tools are hand polished. So whenever you see a very glossy, high finish kind of product, typically there's some girl in China who spent like a week polishing that to get you that very high quality polish, all done by hand. The raw plastic, before it goes in injection molding, looks like small pellets like this. And then it goes into machines that are the size of a car. And about once every 30 seconds, you get a perfect injection molded part, if everything's going well. So this is a sort of a slide that explains why startups may have a hard time competing with Apple. So if you're a startup and you want to do a tool, from the start of your idea, so you've actually got your design done, it takes about 6 weeks average to finish a tool, and then you have what are called the T0 and T1 shots, which is where the first time you actually shoot a tool, it never comes out right. You actually have to shoot it. You look at the plastic; it's crummy. It's got plastic flowing weird places and all kinds of problems in it. And you take it off the tool and you machine it some more, and do a little tweak here and there, and it looks better. You do several of these, and it finally comes out good. But if you screw up, you have to wait another 6 weeks if you want to redo the tool, and it's another $20,000. What Apple would do is they would actually start 5 or 6 tools at the same time. So they would just go ahead and throw, $100,000 on the floor, and they would throw away all but one of the tools. This allows them to explore like 5 or 6 design directions simultaneously in order to, make sure that they can stay on schedule. One of them is picked, and they go to production. And even despite that, I heard last time I was in China, the iPhone 3G, they actually had to redo the tool 3 times. They actually scrapped the tool 3 times because the polish spec was so high on iPhone 3G that the inherent voids and softness of hard tooling steel couldn't be polished to the point where they could get a perfect finish. So Apple certainly spends an insane amount of money to get that finish that you see on those phones, and that's why people ask me how come startup stuff doesn't look as good as Apple's. This is one of the reasons why. I mean, aside from the fact that they've got brilliant designers, but the tooling is really hard too. This again is another example of a tool that I did for a product called the NETV, and you can see here just kind of how high the polish gets on a mirror finished product. It looks, and you can see your face in the steel by the time it's ready to go to production. So. There are a couple things as I go, kind of round out the sort of the hardware slideshow of this that I wanted to sort of say, I guess, to a crowd of people who haven't done hardware. I get this question all the time in meetings: why didn't they put X into the system? It's only $5. It kind of turns out that almost any feature that you want, you can probably go to DigiKey and find it for $5, right? You're like, oh, I want more memory, I want a faster processor, I want a better digitizer, I want bigger speakers, I want a bigger battery. It's only $5. You're selling a $100 product, how come it's not in there? This is why. So as a general rule, if you're doing a $99 product, you want your cost of goods to be about a third of that, so about 30 bucks. $5 is a lot of 30 bucks, by the way, but people don't realize that it's 30 bucks of actual material. Of the $30, you want to keep some of it for yourself, right? So you can actually pay employees and keep the lights on and so forth. So say you take $15 and put in your pocket. The retailer is going to want to actually keep, about that much for themselves. It so turns out that's the way the market works. I don't like it, but that's just a fact of life. If you're sort of a smaller, lower volume equipment manufacturer, you'll be in smaller boutique stores that would take about that much margin to exist. And then they'd round to what I call a magic price. So in retail, they have these price points like $20, $49, $99, $149, $199. And if you tell a retailer, I want to sell something for $107.35, they'd be like, that's not a price. What do you mean that's not a price? I mean, like, no one sells something for $107. The MSRPs are always rounded to sort of these magic numbers, because in a consumer's mind, once they see 3 digits starting with a 1, you can pretty much put anything after the 1, it's all the same price to them. So they always round up to the nearest thing. So then let's go back to, let's go ahead and add $5 to the cost of goods. So now we're at $35 for the product, takes $17.50 from our pocket, retail takes $52.50. You're now just above the $99 point. And then what happens, your MSRP just jumped to $149, right? And so we end up in these very long sort of soul-searching meetings over which $5 feature do we leave on the floor that would really make the product so that we can actually hit these magic retail price points. Another one that I want to sort of talk about, the final one I'm going to talk about on the hardware bit of things, is the high-stakes deadlines. Everyone's familiar who's ship products with the term ship or die. Right? And that's true for software, true for hardware, but it's even worse for hardware because of the sort of the cyclic seasonality of the hardware business. Here is sort of a plot of the volume versus time, and you could think of each of these as like a quarter of a year or something like that. Like 90% of hardware sales happen between Black Friday and Christmas, so Q4 is when you sell, right? It's true for a lot of gadgets. There are a few exceptions to this, but that's basically the truth. So if your schedule had you originally hitting Black Friday and you say, oh, I just want to tweak in a few more features in the software, kind of, refine the UI, do another polishing step, it'll just be a better product, and you ship actually just a little bit after Christmas, you're dead, right? You have to exist another 3 quarters, another 9 months on the fumes that you have left in your bank account, plus you have the whole backlog of inventory you didn't sell during Christmas. Basically, it's the end of the company. And this is one of the reasons why Chumby isn't around today, is because we had these arguments over like, well, the product's not good enough to ship, we can't get it out there. Like, look guys, we have a minimum viable product, it can do an update, right? Ship it. Because if you don't ship it, we're just not going to have money to exist anymore. So from the hardware standpoint, if you're doing a consumer product, particularly a consumer product, the ship deadlines are very, very serious for the company. So this being a Linux crowd, I thought I'd switch from talking about my adventures making hardware to a little bit more about the challenges that I've encountered embedding Linux. There's a whole list of stuff. I'm not going to sort of go into this bullet list individually here. But one of the things that's sort of my quote-unquote favorite part of porting Linux to a machine is that embedded CPUs have lots of weird bugs. Some of my favorites is, like, for example, wrong instructions executed running self-modifying code out of cache. Great. Wrong instructions being executed is always a good thing. This means basically that JavaScript inside WebKit, which is doing some sort of dynamic recompilation, is making self-modifying code. It means occasionally your JavaScript code just crashes and dies and goes away. And this is actually a CPU hardware bug that we had to sort of suss out and put a fix inside the machine to make sure the thing would run stably. You get weird stuff like boot failures below 0C. Fixed, don't run it cold. Okay, great. Another one is default PLL settings are invalid. This one I pounded my head on for like months before I realized was actually the problem. What happened when one of the CPU vendors I had, there's this little frequency multiplier on the inside, would take a low frequency crystal, multiply it up. The defaults they actually had put in the product were wrong. It actually would cause a PLL to be unstable and jitter way beyond spec. And so we were having just these, after running for about maybe a week, maybe about 3 days, sometimes as short as a few minutes, systems would lock up, right? And these kinds of things are incredibly hard to sort of figure out what's going on. It's very subtle, and eventually we figured that out and had to put a fix in the bootloader to correct the PLL settings. Or another one here, faulty logic and store buffer may lead to data corruption. Again, no good. And this one, the fix to this one was again in the bootloader we had to turn off store buffer optimization. So a lot of these really bizarre quirks make porting to a particular product rather difficult. Another fun part of getting Linux to run on embedded systems is the bootloader. Every CPU has its own boot process. People who, when we were taught sort of computer architecture or programming, we know that every computer starts from reset vector, which is at 0 for ARM. And so there's a disconnect between where U-boot is and the reset vector. So a lot of people like to think that life starts at U-boot. Actually, life starts way before U-boot. If your U-boot is stored on a hard disk drive that's over SATA, right, that code from U-boot magically has to appear at location 0 or wherever the reset vector needs to be of your ARM processor. So there's this whole set of code that runs upstream of it that's actually built into the CPU itself that looks at the different media, SD card, I2C flash, SATA, SSD, whatever you want to use, and pulls that code in. And you have to fight with that for a long time to even get your system to run a U-boot. And then once you're in a U-boot, you have no MMU, no DRAM, no nothing, limited exception support, and so you spend a lot of time just trying to get Linux kernel to load. Once you get into Linux, hooray. If you have a device with just a few megabytes of RAM or a very small amount of flash, so Linux will run on devices as small as like 8 to 16 megabytes of memory. You have to have a lot of discipline to keep your Linux fitting in a footprint that big. So in routers, toys, and appliances, every dollar counts, and you just need this constant discipline of auditing and testing. I mean, sometimes people would check stuff in, like make file scripts, or we're just going to do a modification here, and all of a sudden, like, we went from a 16 megabyte image to a 64 megabyte image because they forgot to strip the binaries or whatever it is. BusyBox doesn't save you in these situations. It's just a lot of testing and a lot of auditing for memory leaks and so forth. Flash file systems are typically what are used in the smaller devices. You wouldn't put a hard drive in them. I don't know how many of you know this, but Flash is only good these days for a few thousand read-write cycles. So it's very easy to wear out Flash if you do things like you turn on A-time on your file system. So every time you access a file, it goes ahead and writes back and says, I've accessed the file. No good. No write is actually guaranteed to succeed on Flash. It can fail. So particularly if you're running like a raw iron Flash file system, you have to test a lot for that. And power down corruption is a fact of life. So we have test jigs where we would power on one of our Linux systems. It would run a script. It would start DDing random data to parts of the disk. And then it would commit the data, and then we would just cut power at a random time. And we would do this thousands of times over and over again. Every flash disk will eventually have a corruption problem where it zeroes out random sectors of the disk. This just happens. And so you have to have countermeasures built into your system to prevent returns to go ahead and have safe backup images or re-imaging of certain locations that you know are particularly vulnerable to restore your system. Power management is fun on embedded devices. I don't know how many people have to deal with dynamic voltage frequency scaling on a daily basis, but the basic theory behind it is that power is a function of, this is the only equation I have, a function of capacitance times voltage and frequency. As you lower your frequency, you can lower your voltage, and lowering your voltage gives you a square law of goodness in terms of power reduction. The weird part of this is now I'm handing to a programmer essentially a screwdriver to the potentiometer to the voltage on the CPU, which is never a good idea. The question is, how do you make drivers that do this safe? Like when the guy's testing and he has, I don't know, some point arithmetic error and he starts blowing like zeros or all F's into these registers, you don't want the CPU catching fire and letting out the blue smoke. So there's a lot of work I do upstream of these kinds of things to make sure that we have a sane system before you even give it to the guys to figure out how often to adjust, what to predict, and when high load is coming. Another problem with power management is that rogue processes and kernel tasks can really eat through your power. So even if you've done all your magic optimization, some guy will check in a driver and it pulls the kernel or something like that every tick, right? And so now your CPU, which could sleep, is now constantly being woken up once every millisecond saying, hey, do you have an event? 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 So you have to kind of go through and audit all these things, kind of hash through your daemons, make sure they're not doing dumb things. And then when you allow user apps, like in the Chumby case, people can write whatever they want and load it on it. Man, power consumption can go through. I mean, sure, everyone who owns an Android phone have had the experience of a rogue app just running away and burning through your battery in 4 hours. Suspend sleep is painful. One of the troubles of being an open source and embedded is that people write a driver, they check it in, it's great, but they didn't include suspend sleep support, whoever it is. This is a very, very frequent problem I have. So we end up taking drivers that for different elements, and we have to refactor them to deal with the fact that sometimes you want to actually turn off the peripheral while the Linux is still on, power on the peripheral later, restore its state, and have that all work correctly. And then finally, it's, when you have these small devices, it's just a driver soup. You just have all these bizarre sensors that are plugging into Linux now, accelerometers, temperature, barometers, and then if you're doing robotics, you have to do vision and rangefinders, FPGAs, all kinds of stuff, and you're doing a lot of one-off drivers. And essentially, for the one-off drivers, the guy who's writing it is just you. You don't have a huge support from a community behind it. Responsivity is a big issue on embedded platforms. And as I was saying before, the development community for embedded devices is relatively small compared to desktops and servers. And particularly if you want to do something innovative in the hardware space where you have to redesign redesign a driver, basically it's just you writing a driver by yourself. Every sort of custom small device, you have to think about how you're going to do updates and patches, right? Not everyone can afford to put Debian on a box and just use the great system that's there. And so we have to roll our own update servers, our own package managers, assigning protocols, fail-safe rollbacks, all that sort of stuff has to be tested and brought out for production. So all those challenges, the core challenges, at the end of the day, you want to ship a product, you want to ship it on time, on budget, no bugs, or at least a way to fix them later on. And what it boils down to is that complexity is really your enemy. And when I look at any particular system, the most complex part is always the software, right? Like hardware we can build and I can get it right and we can get it working to a pretty high level of reliability. Software is always the long pole in the tent. And I think it's partially because software is just so quote unquote easy. It's poorly defined, it's highly mutable, a lot of times it's grow not designed, there's lots of feature creep, a lot of this contributes to the complexity of the software problem. So when as a hardware architect, I try to balance performance, cost, and schedule. And in the end, a lot of the choices I make for the hardware are driven not necessarily by user requirements, but what does it take to actually make developers get something done in time. And at the end of the day, once I've defined a box and I've built it, it's the new cage for my developers. I would literally go to a software guy, put a new box on his desk and say, here is your new cage, because like it just has this much memory, has this much CPU, has this much flash, and if you want to get outside of it, you can't. So they have to now work within that particular cage. But you want to make sure that cage is big enough that you can actually get the work done at the end of the day. So I'm going to go through a couple case studies of some hardware we've done where I've had to sort of tangle with some hardware integration issues, some architectural trade-offs, and how they can impact sort of the Linux implementation layer. This is a piece of hardware that I recently made. I call it Kovan. It's a robot controller board. It has a 800 megahertz ARM CPU on the inside. Has an FPGA, 4 channels of motor drivers, 8 analog inputs, 8 digital IOs, has some HDMI ports, battery charger, serial, blah, blah, blah. All the sorts of stuff you need to build an autonomous robot. One of the requirements for it is that it needs to be able to do image processing. And so we were going through a few different architectures we could use for how to glom on the FPGA coprocessor for image processing. If you were to sort of come from a kind of desktop-y environment, the most intuitive way to do this would be to take your system on chip, which is the CPU, you plug the camera through USB into it, you make the FPGA look like a PCI Express peripheral, and you'd call it a day. The pros of this is that there's lots of flexibility on the FPGA can be used. The FPGA doesn't need a frame buffer because it can use the main DDR for that. The problem with this is that the memory bandwidth on DDR really gets eaten up very quickly. On a small embedded device, in this case, we had a 16-bit DDR2 800 memory chip, which means you only get 1.6 gigabytes per second of bandwidth. If you're doing 720p video, it's eating 200 megabytes per second. So you're going to go ahead and take that, you're going to take 200 megabytes per second, flush into DRAM, flush DRAM to FPGA, FPGA back to DRAM, and then DRAM to LCD. Pretty much your memory bandwidth is gone, right? It's not a good idea to really do it this way on a low-end architecture. And furthermore, PCI Express is just hard to do in hardware. So one way to sort of get around this is, okay, let's not attach the camera to the SoC, let's go ahead and attach the camera to the FPGA. This saves us a round trip out of memory, right? So now the FPGA is masquerading to the SoC like an HID device. FPGA will go ahead and take the image data, pre-process it, flood into SoC, and then we can write it to DRAM, go to the LCD, and so forth. This saves a lot on DDR memory bandwidth. A lot of the high-speed data path management is done, and one of the cool things is the driver just looks like a camera driver. So all of a sudden I've taken a big, nasty software driver that I have to write and turn it into nothing more than a camera driver. And that's one of the things that I really like about the architecture. Another way to do this is, in fact, we can just go ahead and move the FPGA in between the SoC and the LCD. And the idea here is that if you're just, whatever comes on the screen of the LCD, you can pre-process with the FPGA and feed back into the SoC through an internal camera port as image process data. This one here, again, saves on DDR memory bandwidth. Again, the FPGA just looks like dev FB. You write a pixel to the frame buffer, it goes to the FPGA automatically, so you're not dealing with a lot of DMA stuff, and it's really trivial to implement. The RGB interface is a very, very simple one to build. And for completeness, this is another place you can stick the FPGA. You can go ahead and put the FPGA between the SoC and the memory. This has been done before. It's very hard to do. We didn't do it because it's very hard, but if you can stick an FPGA between the CPU and the memory, you can do all kinds of funny, crazy tricks on the CPU. In the end, what we did on this particular architecture is that we did the laziest, simplest thing, which was stick the FPGA between the SoC and the LCD. So basically, whenever they wanted to do image processing, they would just take the camera, they would just throw the camera to the screen, and then we turn on the FPGA, and we do image extraction and feature recognition, and then feed that back through an internal camera bus. So it looked basically just like a display in a camera loop to get all the image extraction done. Another question people often ask is when you put an FPGA in a system, how do you configure it? You know, FPGAs are reconfigurable pieces of hardware. You have to bring them up. We used a synchronous serial port from the SoC, so we can configure it in 50 milliseconds. The FPGA itself is presented as a block device, so it just looks like dev FPGA. You just cat your configuration file to dev FPGA, and then you're done. That's the full extent of what you need to configure an FPGA. Use some IOCTLs to go ahead and reset the FPGA or check the done status. No special executors or scripts required to get going. Another thing we did is that because FPGAs have many pin-compatible variants you can put into the single slot, we have to figure out which FPGA we're talking to prior to doing the configuration. So use a set of GPIOs with JTAG-based ID code looping. We go ahead and wiggle the JTAG lines and see what ID codes come back. And from there, we can automatically switch multiple FPGA types based upon what the customer build is. So I'm going to go through one last case study here. This is the NETV. NETV is an embedded Linux product that I had made that goes between a video source and a monitor. And the idea behind it is that you can go ahead and overlay a piece of video on top of a background video that you're watching. The way it's done is essentially we actually create inside a frame buffer a WebKit page. It's a Chromeless kind of WebKit, a Chromeless web page. It's all done in Ajax, so it's done with JavaScript and so forth running inside. And we set the background to a pink color. Whenever we see the pink color, we replace that pixel with video, and then everything that's not pink gets overlaid on top of the video. Seems pretty simple, but it's actually not that easy because most HDMI video is encrypted with HDCP. And in order to, if you were to do this by decrypting video, pixel by pixel, and then replacing them, you actually run into a legal problem in the United States. I don't know if Australia is an issue, but in the US, you can get potentially sued for just overlaying video on top of video. So the solution we came up with was to swap encrypted pixels, which relies upon dead reckoning the timing from the timing information relayed inside the video stream. This is basically the overview of how it's done. We did a man-in-the-middle attack on HDCP. There's actually there's a weakness in the exchange of keys and how it's done, so that you can actually extract the master keys. And by observing the handshake between the two, you can actually figure out what the transmitter cipher key state is. So then we would init the transmitter's key schedule to be identical to that of the upstream video source. And then we would encrypt our local frame buffer to the same key that's being used in the transmitter, which allows us to do pixel by pixel synchronization and swapping of data. So at the end of the day, if you had so at the end of the day, if you had this sort of encrypted video coming from the source, you have your unencrypted video in the frame buffer, you have your cipher state here, you hash them together, XOR them together, and then you can just go ahead and swap those pixels out when they're decrypted. You can turn a 1 into an I on the screen. The architecture that we use to do it involves an FPGA that sits in line on the HDMI bus, and then a little Linux computer here, and the FPGA just looks like, again, in the Covan case, the FPGA just looks like an RGB LCD interface, so it just gets data in from the frame buffer. The question is how do we get real-time pixel swapping in an embedded Linux machine? We have to synchronize the frame buffer and the redraw rate inside of the Linux machine, pixel by pixel, accurate to the incoming HDMI stream. This is the actual implementation of the hardware. So again, an 800 megahertz Linux computer. I like to reuse my IP a lot between projects, as you can tell. And there's an FPGA. Very, very simple, very low cost. Excuse me. The challenge is that the pixels have to be exactly timed to video pixels, and we're using DevFB0 of the Linux computer to get the pixels. And if we just went ahead and we looked, for example, at the vsync interrupt and tried to time the Linux computer's sort of redraw based upon that, there's way too much interrupt jitter on Linux, right? It's tens to hundreds of pixels. Furthermore, beyond that, the crystal oscillator, even if we get that perfectly on, say somehow magically we can get Linux to not have interrupt jitter, the crystal oscillator of the local sort of CPU itself has a long-term drift of 100 pixels per frame, right? Something like that. Just that's based upon the pure PPM accuracy tolerance of a crystal. And so finally, if we don't do something special, we're going to have like jitter and drift on the screen without tight synchronization. So this is how we solve the problem. First, for the pixel clock for video, we actually source the pixel clock not from the graphics engine, we actually take it derived from the video stream. So we actually have a PLL that goes ahead and looks at the incoming clock, derives a clock from it, and then we use that to clock the frame buffer. So that's a hardware hack. Second thing we have to do is that because HDMI supports multiple video resolutions, we actually have to dynamically change DevFB0's property to match the incoming video resolution. So if it's 480p, we have to set the frame buffer to 480p, 720p, 1080p. These all have to be dynamically derived and matched by the local computer. Then whenever we have a VSync, we go ahead and we start the LCD DMA based upon when we get a vertical interrupt. Basically, we do a mini gen lock on inside in software. And essentially, we look at the historical pattern of VSyncs, and we wait where we think the next vertical frame will start, and we go ahead and start the frame buffer reading out at that point in time. Of course, Linux sort of ability to get a low jitter interrupt is pretty bad, so we had to add an elastic FIFO to buffer a few lines of video to absorb all the VSync jitter. At the end of the day, this is what it looks like on the inside of the FPGA. There's a FIFO that takes the video coming in, line by line. We encipher it. We have a multiplexer that picks the pixels, a chroma key detector, and then the man-in-the-middle mechanism up top. So a little bit about the development environment. A lot of people who haven't done embedded computing oftentimes ask me, what does the development environment look like? For this particular project, this is the tool chain that we picked. A lot of times we use these very stripped down distributions called Angstrom. Some people have heard it, some people haven't. It allows me to build a Linux image that fits in tens of megabytes if I want to. It's all brought together with a system called Open Embedded. Open Embedded is an integrated sort of package management / build / update deployment tool. On top of Angstrom, we run WebKit, and then on top of that, we were putting our JavaScript widgets in GitHub. So if people want new widgets, we just do a git pull, and new widgets would arrive in a directory, and you could run them and get new content on the screen. And finally, we had an update server that we put in EC2 in the cloud. And incidentally, everything below this stack is also open for this particular design. You can go to my website, you can download the FPGA Verilog, the PCB, the plastics, you can build one yourself. So the philosophy, excuse me. I live in Singapore, so this is very dry for me. I don't have the ability to make mucus, apparently, anymore. So the development philosophy is we want to get people up and running in half an hour, right? One of the problems with building for ARM platform is that the ARM device itself isn't powerful enough, at least not until about today, for you to really do a kernel build on the machine. I mean, we can build a kernel on it, but it takes like an hour or two. It's really painful, right? So you really want to have a cross-compiler set up. You want to have your source control, you want to build management, all this sort of stuff. If we tell someone, hey, you can go ahead and build an image, it will take them a minimum about a day or two to pull down all the source and build everything from scratch, which is a really huge barrier because it turns what ought to be a weekend project into an epic task. So our solution was we went and we tried to take all this, package it up, and put it into an Amazon EC2 image that anyone could then sort of rent and plug into. So you could go ahead and grab your EC2, launch an AMI. It would come with its own little local Git repo. And there was this sort of wonderful sort of auto build system. So whenever you did a Git commit, it would go ahead and rebuild the image for you and spit out a ROM image. The neat thing about this system is that once you actually spat out a ROM image from your EC2 server and you image it onto a device, that device is now keyed to look to your personal EC2 server for updates. So now you actually have a fully production-capable system. You can go ahead and sell this device as long as you keep your EC2 server up. You can have a script on the inside that checks for updates, and all the units in the field will go ahead and grab updates from the server that you've started from in a half an hour. One of the problems is that actually, well, the system did enable a few more developers, but one of the problems is that EC2 instances are really, really slow unless you pay a lot of money for them. And the developers' sort of profile is they want like 16 cores for about 15 minutes, and then they want no cores for like several hours. So unfortunately, EC2 was a really bad match for the problem, because in order to get 16 cores, you're paying a shitload of money. It's hard also to convince people to drop a credit card number into Amazon just to try out EC2. So they had these micro instances that were free, but they would crash all the time when building because they'd run out of memory. And so we had a lot of people trying to convince them this was actually a good solution. A lot of professional developers anyways prefer to roll their own solutions, so like, screw what you did, I'll make my own build machine. And another amazing thing is that people who want to use this solution, hardware companies, it was very hard to convince them how difficult it is to do update servers and to build their own updates. They would be like, we'll just deploy a product and then updates will happen, right? They just get it from somewhere. And I say, well, this is your own custom image. We don't have your code. We can't do these updates for you, right? And they just would not understand why it's not possible for me to push updates for them. So in practice, it didn't work out as well as we'd like it to, and this is one of the things I want to try to improve in the future for embedded development is how to get these things going. I think there's actually some talks later on I saw on the list that may be actually talking about something like this. I'll be stopping in to hear it. So the takeaways from this talk would be, if you're doing embedded Linux and computer electronics, particularly if you're, from my standpoint, doing the hardware-software co-integration, it's a multivariable optimization of a very quirky system for many things. Cost is always king in hardware, and you have to really sort of fine-tune the balance of extra hardware capability versus more software developers. $2 will buy me twice as much RAM. And if I'm going to sell 100,000 units, it costs me, that's $200,000 for the life of the time of the product. That only gets me like 1 or 2 software developers or something like that, right? So there's a sort of a trade-off between how much RAM I put in a product versus how much I really want to make the software developers have to optimize their code. Complexity is something that I really try to avoid. So I try to optimize my hardware architecture choices to be as lazy as possible and to reduce software development risk. Sustainability is always an important thing to remember. So you have to have a system and a way to do updates and patches for your custom distribution, because essentially that's what it is for an embedded machine. And then enabling community involvement is very important. I really like to get more people involved in the projects I do, but you have to really bring a lot of people in who haven't necessarily done embedded development before, who are interested in your product, and so you have to package up an unusual system in a desktop-friendly format. And then finally, you have to always keep in mind this time to market. You have to ship or die. And that's it. Thanks for everyone for listening.
Thanks very much.